Alright guys, in this video we're going to be talking through a few example problems dealing with standing waves. The first one dealing with standing waves inside of strings like a guitar, and the second example problem dealing with standing waves in columns of air. So let's look at standing waves first in a guitar. Number one says a guitar has 0.065 meter long strings fixed at both ends. In the top string on the guitar, the lowest possible frequency which creates a standing wave is approximately 82 Hz. The lowest possible frequency which creates a standing wave is called the fundamental frequency. So the fundamental frequency of the string that we're talking about is 82 Hz. This is the lowest pitch note this string will produce. So the lowest frequency standing wave that creates a note on a string is called the fundamental frequency. So A says, draw the standing wave on the diagram above, which is associated with this fundamental frequency. And so if we have a string that's fixed on both ends, remember that there has to be nodes, one on either side of a fixed end, in any possible standing wave that we draw. And the lowest frequency is going to have the largest wavelength. Remember our wavelength and frequency equation. Wavelength is equal to wave speed divided by frequency. And if you have the smallest frequency, if you're dividing by a smaller number, the smallest number, then you're going to get the largest wavelength. And so what's the standing wave that has the largest wavelength for a string with two fixed ends? Well, that's that first possible standing wave where we have half of a wavelength that fits inside of this length. So if we have our two fixed ends, a standing wave with half of a wavelength would look something like this, where the ends are not shaking back and forth from equilibrium, but in the middle, so half the length of that string, we have an antinode, so the string is shaking back and forth like this. Part B says, what is the speed of the sound waves moving through the string which create the standing wave? As long as the tension of the string is not changed, this will be the speed of all the waves moving through the string. So if we introduce a disturbance, there's going to be waves that move through here, and what gets created is the standing wave. And so the standing wave doesn't appear to move because it's standing still, right? That's why it's called a standing wave. So the antinode location stays here, but remember, that's the result of waves that are moving through the string, bouncing off the fixed ends and interfering constructively and destructively, and they're moving through that string at a particular speed. So let's figure out what that is in meters per second. Well, if we go back to our equation up here, wavelength is equal to the wave speed divided by the frequency, or if we solve this for the velocity, we multiply each side by frequency, we get that the velocity of the waves, or the wave speed, is equal to frequency times wavelength, right? So we can calculate the velocity of the waves moving through there if we just take the frequency of the wave multiplied by the wavelength of that wave. Well, we said for the fundamental frequency, the frequency of the note that gets created by that is 82 Hz, which means the frequency of the waves that create that standing wave are also 82 Hz. So we multiply our 82 Hz times the wavelength. Well, we've got a 0.65 meter long string, and how much of the wave fit inside of that length right there? Like from each of the fixed ends, this right here is only half of a wavelength from one fixed end to the other fixed end. So if half of a wave fits in 0.65 meters, what's the full length? Well, it's going to be exactly double that. So 0.65 times 2 is 1.3 meters. So let's do that over here. So if a half of a wavelength is equal to the length of the string, half of a wavelength fits into 0.65 meters. This is essentially an equation. 1/2 wavelength equals 0.65 meters. So let's solve for what that wavelength is. We'd end up multiplying 2 on each side, so the 2 cancels out on the left-hand side. And so the wavelength is going to be 2 times 0.65 meters, or the wavelength is going to be 1.3 meters. So now we know that the wavelength that's moving through the string is 1.5 meters. the string is vibrating at a frequency of 82 hertz. And so we can figure out what our velocity is. It's just 82 times 1.3, which is 106.6 meters per second. And actually, that's the speed of any pulse or periodic wave which moves through that string. Remember, the speed of a wave moving through a string is affected by the tension, and if the tension remains constant, that means if one standing wave is created we can figure out that the waves are moving at this speed, that means that's going to be the speed of any waves moving through there, even if we're creating different types of standing waves. Okay, part C says, draw 3 more possible standing waves on the diagrams below, which are possible on the same string. So on the same string, we know that, like we just said, they're all moving at this speed, 106.6 meters per second, because the tension stays constant. And this is the first possible standing wave. That's the standing wave with the lowest frequency, which will produce the lowest pitch. Well, just like in the video that we talked about previously, there's lots of other standing waves which are possible on that same length string. So if we have the same length string and they're fixed on both ends, remember, any possible standing wave has to have nodes on the ends. So it's going to be one on the top and one on the bottom since it's oriented like this. And the first one, looking up here, it just had 2 nodes and then one antinode in the middle. If we want to figure out the next possible one, all we'll do that in the one on the left here, is draw an additional node. So instead of having 2 total nodes, we're going to have 3 total nodes, spots where the string stays at equilibrium. So we're going to draw that in the middle of the first 2 like this. The second possible standing wave will have 4 nodes, and all the nodes in any standing wave have to be equally spaced. So if we have 2 here and we want to draw 2 more and evenly space them, then there's going to be a node like 1/3 the length of the string. Here a node was like 1/2 the length of the string. And the next possible standing wave will have a total of 5 nodes. So of 1, 2, and if I want to space equally 3 more, there's 1, 2, 3. So the nodes are 1/4 the length of the string. So whenever you're drawing standing waves, I find it easiest to draw the node locations first and then fill in what the standing wave would actually look like. And so since we have to start at a node, we start at equilibrium. And I'm just going to draw out a sine wave that's going to go on one side of equilibrium, the other side of the equilibrium, and then back to equilibrium. So at one instant in time, the string would look like this. And remember, it's going to kind of vibrate back and forth at each antinode location. So now I'm going to sketch that same type sine wave, but kind of flip-flopped horizontally. So it looks something like this. So we have the antinodes in these 2 locations. We've already marked the node locations in red. Well, let's just do the same thing now for each of the other 2 possible standing waves. So I'm going to start here at equilibrium. I'm going to go to the left of the line, to the right of the line, to the left of the line, and then I'm just going to kind of flip-flop that like the last time. So we have our 4 nodes, and we have 1, 2, 3 antinodes. And then we'll do that for our last one. So we're going to draw it to the left, to the right, to the left, to the right, and back. Remember, it has to end on equilibrium, so that's how the string would look at one instant in time, and then another instant in time, and kind of be flip-flopped horizontally. And I'm just drawing a dashed line to show like that's what the string looks like at another time. So we have 1, 2, 3, and 4 antinodes. Spots that are shaking at maximum displacement from equilibrium, and then 1, 2, 3, 4, 5 nodes. And so this is the second possible standing wave, the third possible standing wave, and the fourth possible standing wave on a string that has 2 fixed ends. The last part of this example says to calculate the frequency of the sound wave produced by the standing wave drawn in the middle guitar in part C. Is this a higher or lower pitch than the fundamental frequency? So remember, with this standing wave up here, when there was a half of a wavelength that fit in there, they were all moving at this speed, 106.6 meters per second, the frequency that the standing wave was vibrating at was 82 hertz. So this thing was shaking back and forth 82 times each and every second. And every time it, moves up and then down, it's, when it moves up, it compresses the air right here, and then it kind of draws it away when it goes down, compresses it. So it's going to disturb the air at 82 cycles per second, which means it's going to produce a sound wave which moves away from the guitar string that's moving. And, they're moving away from the guitar string at that same frequency. So it creates an 82 hertz sound wave. Well, if we're looking at the middle one right here, that third possible standing wave, when these guys are shaking back and forth, they're going to be shaking back and forth at a different frequency. So that's going to create a different frequency standing wave. And if the frequency goes up, that means we're going to hear a higher pitch. If the frequency goes down, we're going to hear a lower pitch. It's going to sound like a lower note. So let's find out what frequency is associated with this. Well, if we're solving for the frequency, we're going to be looking at our wavelength and frequency equation that we've already used and referred to. Wavelength is equal to wave speed divided by frequency. And what do we know? Well, we know the wave speed. Doesn't matter what frequency the things shake at, because the string is at the same tension. The waves are still moving at the speed we found in part B, 106.6 meters per second. We're trying to find the frequency, and so if we can figure out, well, what wavelength needs to be created that sets up this particular standing wave, then we can solve for frequency. Well, let's look at the diagram above here. In this length string, which is 0.65 meters, that's what the problem statement said before. So from here all the way down to there is 0.65 meters. And how many wavelengths, or whole or partial wavelengths, fit in that length? Well, if we start down here, if we were to trace out one wavelength, we start here, we have to go to the left, to the right, and back. That's one wavelength. And if we go one, that's like right up here from that node to that node is just half of a wavelength. So in this string, there's 1.5 wavelengths that fit in that length string, which creates that particular standing wave. So if we know 1.5 wavelengths is 0.65 meters, we can figure out how large one wavelength is. So let's just do that down here. So we know that 1.5 wavelengths is equal to our 0.65 meters. So wavelength, let's divide each side of that equation by 1.5. Wavelength will be equal to 0.65 meters divided by 1.5. So the wavelength of the waves moving through that string is 0.65 meters divided by 1.5. It's about 0.433 meters. Right? That's less than 0.65 meters. So let's now plug that back into our frequency and wavelength equation. So if we have 0.433 meter wavelength, they're moving at that speed, 106.6 meters per second, and we're solving for frequency. Do a little bit of algebraic manipulation to solve for frequency. First, we have to kind of get it out of the denominator, so multiply each side by f. When we do that, f cancels out on the right side, and we get that the frequency times 0.433 meters is equal to 106.6 meters per second. Since we're solving for f, let's now divide each side by 0.433 meters. So that cancels out on the left side, so we get that frequency is equal to 106.6 meters per second divided by 0.433 meters. That's going to give us a frequency. So 106.6 divided by 0.433 gives us a frequency of about 246. The units would be, meters would cancel, so you'd get units of inverse seconds. And remember, an inverse second is the same thing as a unit for hertz. And so we get something that looks like this. And remember, the original frequency was 82 hertz for that first possible standing wave. And the third possible standing wave is vibrating at 246 hertz. That's a higher frequency, so that is going to be a higher sounding note, or it's going to be a higher pitch than the fundamental frequency.